Hey everyone, welcome back to my channel EduVibe. Today we will start with the next topic of forces and fields, which is the electrical wheels. So in the previous lessons, we will cover the electrical attractions, electrostatic force, we cover the Coulomb's law, but now they are the more type of a theory part we done. Now we will start with the original unit, like a unit which start from here, starts from the electrical fields. We will cover electrical fields now, electrical forces, we do the vector analysis too, we do more and more things in the concept of the electrical. Now we main focus on the electrical fields, then we main focus on the magnetism. So let's start with this electrical fields. So this is your new topic for you. So let's do by like meaning of first. So the charged object is surrounded by an electric field which has both magnitude and the direction, which means this is the vector field. So this charged object is always surrounded by the electrical fields. And if the object is charged and the electrical field has both the magnitude and the direction, so that means this is the vector field, or you can say this is the vector quantity too. So in case of the fields, we're talking about this a vector field. So, to determine the strength of the electric field, when you determine the strength of the electric field, when you asked to determine the strength of the electric field, so we have to consider the positive test charge. So, positive test charge is always used. So, what is positive test charge? It is a type of a charge which we have want to get the electric field strength. The positive test charge name suggests that this has the positive charge on it. So, to determine the direction of the electric field, so we will know that how what is positive, so we know that how we can calculate. But we firstly we will do the conceptual aspect that how can they do this. So the direction of the electric field can be determined. We observe what happens to the positive test charge in response to source charge. So the positive test charge is always positive, and the source charge is positive or negative. And how they respond to the positive test charge is related to how can we find that direction of the electric field or the strength of the electric field. So the test charge moves is the direction of the electric field. When the test charge moves, whatever they move away, they move towards. So this will tell us what is the direction for this. So so there's a two type of source charge, as I just told you, that negative source charge and a positive source charge. So the negative source charge, the test charge will move towards it, so it attraction. So if there is a negative, so as I told you that this is if negative and the test charge always positive. So when positive negative is there, so it towards it, so it's do attraction. Unlike charges attract each other. Then this means the electric fields for the negative source are directed towards the source charge. So the electric fields also directed towards the source charge as the test charge do. The same the direction we will do. We will learn about the electric fields that they also directed towards it when there is attraction. Where there is a repulsion, so there's opposite aspects. So test charge will move away from it, as we know that this positive now and this is remain positive. So now the positive will do repulsion. So this means that electric field for a positive source charge is directed away from the source charge. So again this is now away because the repulsion will happen with positive and positive. So that's how the practical work do through the diagrams. So that's how we can figure out the direction of the electric field is the same as the direction of electrostatic force. As I told you that electric field is depend on the test charge or source charge, attraction or repulsion. The electrostatic force also depends on the electric field. If electric field towards it, so electrostatic force also towards it. Away from it, so away from it also. Acting on the test charge due to the source charge. So as I told you, this is the source charge which is a negative, and this is positive test charge always. And if this is positive and negative, so it towards it. So it goes towards it, and the electric field, if I mean the electric field, so the electric field also towards. So this is the electric field notation that E suggests electric, and this is the magnitude, and this is a vector, so we put arrow on it. And this is the force. The force also towards it. So, and if this is positive source charge, so this positive test charge moves away from it, and if it moves away, so force goes away, and from source charge, the electric field also moves away. So that's how the relationship between the forces and electric field, the electrostatic force and the electric field, always do what the test charge do, is towards other. So from here we can say that the electrostatic force and the electric field are related. How this can be related? We have one formula for this. How can we derive this formula? You doesn't have to know this, but you just know this. What is that formula? So this is electric field is equal to Fe. Fe is rather the electrostatic force divided by Q. Q is the charge. In that case, the Q is the magnitude of the test charge. The test charge we have over there, this magnitude this Q has. That F is the electrostatic force and the E is the electric field. E has the units of Newton per coulomb, or the V volt per meter. This volt per meter we will know when we do the potential energy, electrical potential energy, when we know this. Now that this formula is not satisfied with that when we do with the source charges. Basically, we want for the source charges. So what can we do now? So as we know that this is our formula, what can we do? We replace this test charge with the source charge. So when we replace this, we get, and source charge is Q2, we suggest. We name it as Q2, we let it as Q2. And when we let this, and this is Fe, that Fe is equal to what? We all know that we do the previous lessons, so F is equal to this. So we put this over there upon Q2. Take Q2 cancel out. What we get is KQ1 and R square. Now that Q1 is our source charge. From here we get the formula for the electric field. So electric field is equal to K times Q upon R square. That E is the magnitude of electric field, Newton per coulomb, or the volt per meters. This is a Coulomb's law, as we all know the case, and this is the value for this. R square is the distance between the source charges and the test charges. Okay, and this is the magnitude of the source charge. This formula, we will not use this formula anymore. We use this formula to just drive that formula for electric field, which includes a K. So before dealing with that, the one thing more, the electric field lines. So if there's any force, if there's any field, so they also have some lines too. So for a positive source charge, as we will have a for positive source charge, the electric field lines start from the charge. They start from the charge and they stand radically to outwards towards the infinity. Like they goes infinity like this. They start from the charge and go infinity in the positive source charge. The negative source charge, the electric field lines start from the infinity like this, and they move radically inwards and terminated on the surface of the source charge. So this is a negative charge and this was in the positive charge case. So electric field lines also do like this type of thing. So let's deal with the formula which we done for the electric field. So how can we find that if we determine the electric field of an alpha particle at 3.87 to 10 raised to power minus 10 meters from the alpha particle? So firstly, we have to know what is alpha particle. So on your data sheet, you have alpha particle, and alpha particle has the charge of 2 positive. This is a charge for alpha particle, and the charge is 2 positive, which means that charge, if we want to calculate, so it is 2e. So always, if we have some electron has 1e, alpha particle has 2e, so that 2e we have to like this. That e is our elementary charge, as you all know that. So this elementary charge is 1.60 to 10 raised to power minus 19 coulombs. When you calculate the q for alpha, you get about 3.20 into 10 raised to power minus 19 coulombs. So now this is a q you have to use because we didn't have u. And this is our r and k you have, and we have to find the electric field. So KQ upon R square. That E is equal to 8.99 into 10 raised to power 9 Newton dot meter square, Coulomb square. Q is 3.20 into 10 raised to power minus 9 coulombs divided by 3.87 into 10 raised to power minus 10 meters. So when we solve this, when we divide by, we get about 1.92 into 10 raised to power 10. This is in Newton and Coulomb. So we also, this is a vector quantity, so we have to know that there is dash in there. So the alpha particle is in positives. This is our source charge. So if this is our positive and our test charge is also positive, so electric field goes what? Positive, positive goes away. So this means this away from alpha particle. So if there's a vector, if they ask or not, you can write. If they ask particularly, so you have to write. If they not ask, so it's optional for you. So that's how you have to use this formula. We will do more complex questions when we do practice questions of this lesson. And this type of question you get in the MCQs automatic often. Like this is the important formula you have to know. We get the graph questions too. We'll do a graph questions in by next lesson, and we will do that. So one more thing you have to know as example point of view. So they tell us that determine the magnitude and the direction of the electric field that is 14.0 centimeter from a plus 9.70 microcharge. So microcoulomb charge. And here's the quantities that are different. So we have to convert those quantities now. So that centimeter should be in meters. So we have to divide this by 100, which is 0.140 meters. This 9.70 is micro, has the value of 10 raised to minus 6 coulombs. And when we put this in, so KQ upon R square, so K is 8.99 into 10 raised to power 9 meter Newton meter square, Coulomb square. This is 9.70 into 10 raised to power minus 6 coulombs divided by 0.140 meter square. So when we calculate this, we get about 4.45 into 10 raised to power 6 Newton Coulomb. Now they mention we want the magnitude and the direction. We find the magnitude, which is this, and we have to find the direction too. Now this is like positive charge we have. So positive test charge we have. This is a source charge. And the test charge is always positive. So they move away from the source. So away from source. So you have to mention this like this. If you want to make diagram, you want. So that's how we can deal with the oceans. And if there's a separate units, so we have to deal like this. So that's all for this lesson. I hope you understand this, how can the electric fields are doing, and we will more looking for the electric fields in upcoming lessons. The electric fields is like the big topic. We do some vector analysis, vector addition in the next lesson, which is like a very important topic. You get the return response from this oftenly. And so learning is simple with EduVibe. Learn smarter but not harder. Please like, share and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till then, stay connected with EduVibe.